As I said earlier, it's because of the tendency of the material to get compressed, and this phenomena is called as electrostriction. This is a bulk phenomenon. It's a property of the bulk property of the material. It has nothing to do with the specific molecular arrangement or anything like that. This interaction of optical field with the acoustic waves results in downshifted Stokes frequency or upshifted in wavelength. The process becomes stimulated if the input power is larger than the threshold value. So, what is the phenomena? How do you explain the phenomena of stimulated Brillouin scattering? So, this is what happens in the system. So, let's say this is the core of the fiber. There are these natural thermal vibrations happening in the system. These thermal vibrations could be of different frequencies. It could be moving in different directions inside the fiber, right? So this omega, which represents the acoustic frequency. So this omega represents the acoustic frequencies. For now, this omega is a variable because it's a thermal noise, so you have all kinds of frequencies present in the system. Now, in that system, let's say you have incoming light. Let's represent the frequency of that incoming light as omega p. So, what happens is this omega p, let's say corresponding to omega p, let's say its wave vector is kp. So, this incident light, which is represented by this wave vector kp, interacts with all these randomly moving acoustic waves in the system. So, let's consider a specific random direction of this acoustic wave. So, let's consider a random direction of this acoustic wave. So, this interacts with this acoustic wave, resulting in, let's say, a scattered wave. So, let's say this is some direction of acoustic wave. So, Ka represents the wave vector corresponding to the acoustic wave, resulting in a scattered wave. So, with a frequency omega s, which is the Stokes frequency, which is equal to omega p minus omega. The Stokes frequency is downshifted, we always saw. So, corresponding phase matching condition for this interaction to happen, we have derived similar phase matching condition in four-way mixing. Using the same idea, you should have Ks is equal to Kp minus Ka, where Ka is the wave vector of the acoustic wave. So, this is the wave vector that represents the process, or this is the vector diagram that represents the phase matching condition, where you have Kp minus Ka giving rise to Ks. Okay. Now, this phase matching condition is actually directly coming from this energy conservation condition for this scattering process, and this phase matching condition is important because you are talking about interaction between two waves mediated by the medium, and whenever you have that process happening, when we discussed the chi-3 nonlinearity, we realized that the phase matching condition is important. Now, the only difference here is that the phase matching condition is with the medium, the acoustic wave vector of the medium. Now, what is this Ka? Let's write what this Kp is. Kp is omega by c, refractive index of the corresponding to the pump. Ks, magnitude of Kp, magnitude of Ks is omega by c, refractive index of the Stokes. Now, assuming that the pump and the Stokes, the frequency shift is very small, we will prove that it is very small. Assuming that they are small, we can say that Np is almost equal to Ns, which is almost, let's say, equal to N. Similarly, Ka is the wave vector corresponding to the acoustic frequency, that is omega divided by c, Instead of C, I should write, because it's not electromagnetic wave, it's an acoustic wave. So it is acoustic wave velocity VA in the medium. So VA is the acoustic velocity corresponding to the frequency omega, capital omega, in the medium. At the moment, this capital omega is a variable, but now that I apply this phase matching condition, it will so turn out that only certain omega is allowed. Why? Because if this vector equation needs to be satisfied, now I can use the triangle law of vector addition and say that my Ka magnitude must be equal to, if it satisfies this condition, the magnitude of Ka must be equal, must satisfy this equation. It should be magnitude of Kp square plus Ks square minus 2 magnitude of Kp, magnitude of Ks, and cos theta, where theta is the angle between Kp and Ks. This is simply applying the triangle law of vector addition. So I can just substitute these numbers. So I get omega square by Va square is equal to omega square by C square, twice of that, because this is omega p and this is omega s, and I am assuming omega p is approximately equal to omega s. Again, I will tell you why this is still true. Times n square minus 2 omega square by c square n square cos theta. So this is 2 omega square c square, omega square n square over c square 1 minus cos theta, which I can write it as 4 omega square n square by c square sine square theta by 2, which means I can now, so let me call the omega that satisfies phase matching condition as omega b, right? So omega is that acoustic frequency that satisfies phase matching condition. So that is omega b. In this case, omega b divided by Va must be square root of this, which is 2 omega n by c sine theta by 2. Okay. So what does this mean? It means that my omega b is nothing but 2 times Va times this, and omega n by c is wave vector k. So this is 2 magnitude of Kp Va sine theta by 2. Now this is a very interesting result which tells us so many different things about stimulated Brillouin, about Brillouin scattering. So when so what does it say? I have my incoming pump with a frequency omega p. It interacts with all possible frequencies omega, but it turns out that it can phase match with only a specific frequency omega b, which is given by this number. Now that greatly depends on theta, which is actually the angle between Kp and Ks. Now in a fiber, we just said that you can have either the scattered light can propagate in the forward direction, for which theta equal to 0, or the light can propagate in the backward direction, for which theta is equal to pi. So if theta equal to 0, obviously omega b is equal to 0, and omega b is equal to 2 magnitude of Kp times Va for theta equal to pi. So it means that I can have an omega b which is 2 magnitude of Kp times Va for theta is equal to pi. Means that the pump that is propagating in the forward direction in the fiber can result in a frequency shift only for this theta, which is the angle between Kp minus Ks at pi, which means for a phase matched Brillouin process to happen, if this is the direction of Kp, my Ks will always be in the opposite direction. Corresponding to that, where is the acoustic wave? If Ks turns in the opposite direction, it means that your omega Ka is in the forward direction. This is the acoustic wave vector, right? So this is the process that is allowed in an optical fiber. You may have scattering in the forward direction, but there's no frequency shift corresponding to that scattering because your omega b equal to 0. There's no shift in frequency. So it simply means that the bottom line is that whenever you have Brillouin scattering supported in an optical fiber, it means the Stokes is propagating in a direction opposite to that of the pump. So if you're trying to send the light in the forward direction, the Brillouin scattered Stokes light, which is downshifted in frequency, propagates in the backward direction because of the interaction of this pump with this acoustic waves that is propagating in the forward direction. That's spontaneous process. Now, how does a stimulated process happen? So you have the pump frequency propagating in the forward direction. This results in the generation of a Stokes frequency which is downshifted in the backward direction. So you have two frequencies which are counter propagating in the fiber with a very slight frequency difference. We still don't know what exactly is the frequency difference, but we know how to calculate this. Okay, let's first try to calculate this frequency difference. So let's say omega b is, let's say we try to calculate the magnitude of this. So this is twice. Kp is again 2 pi divided by lambda times n, which is n effective at that wavelength, times acoustic velocity. Now, acoustic velocity in a fiber is approximately 5,960 meter per second, right? So you can calculate this for lambda is equal to 1550 nanometer, and this number turns out to be something like 11.1 gigahertz at 1550 nanometer. So which means the frequency shift that we are talking about is only 10 or it's okay, depending on the type of the fiber, the composition of the fiber, etc. The acoustic velocity would slightly change because of which the Brillouin frequency shift could be anywhere between 10 to 12 gigahertz in a single mode fiber. So we are talking about only a shift of about 0.08 or 0.09 nanometer as far as the pump frequencies or pump wavelength is concerned. So now let's see how this process builds into a stimulated process. So you have omega p, you have omega s, which is downshifted by about 11 gigahertz, but it's propagating in the opposite direction. Now, whenever you have two waves propagating in the opposite direction in the same medium, you have a beat generated. You have a beat generated at the sum frequency and the difference frequency, which means the material is actually responding at the sum frequency and the difference frequency. Now, in the difference, sum frequency is too large, it is not in the range of acoustic waves. But the difference frequency is, because the difference frequency we know is 11 gigahertz. So you have regions along the core where the electric field is high and low, and it is also moving because your pump is moving in the forward direction, Stokes is moving in the backward direction. So the beat is also moving in the forward direction. But it also has a frequency 11.1 gigahertz. So you have a strong electric field and a weak electric field kind of scenario set up. And this is where our electrorestriction comes in, which means whenever you have a large electric field, the tendency of the material will be to compress in that. When you have an electric field, that compression would result in a reduction in volume, which means the refractive index, the optical density will increase. So this is as if you have generated a grating, which is like a large refractive index, a small refractive index, a large refractive index, and so on. And this grating is moving, and the period of this grating is corresponding to lambda, which can be related to your omega. So now the pump is actually seeing a refractive index grating, right? You have light going in, you have a variation of refractive index that this light is experiencing. So obviously there is scattered light, and that scattered light, because it is a grating that is moving in space and there is a change in time, you have the scattered light that is moving in the backward direction because the grating is moving in the forward direction, and it is downshifted in frequency because the grating has a frequency 11.1 gigahertz. So this results in the buildup of Stokes in the backward direction. You see, so initially you had the phase matching playing a role to generate the spontaneous Stokes field, but once the spontaneous Stokes field is set up, there is a beat generated, and then this becomes a positive feedback. The electrorestriction poses a refractive index contrast, so the pump gets scattered by this grating, and so you generate more Stokes. And because the Stokes is generated with more strength, the beat becomes a little more stronger beat, right? The beat becomes, the depth of modulation of the beat increases. This means that the grating has become, the contrast of the grating becomes much larger. It becomes a stronger grating, and so your Stokes starts increasing in strength. So this is how the process emerges from a spontaneous process to a stimulated process. Okay, but doesn't matter whether it is a spontaneous process or stimulated process. In both the cases, your Stokes gets shifted with a frequency omega. So this condition, omega Stokes is equal to, one has to be very careful here. This omega b is in gigahertz, and omega s is equal to omega p minus omega. When we write this relation, you have to be careful that this is in 2 pi radian. So this is not omega b, this would correspond to FB. So FB is 11 gigahertz, corresponding to that you have an omega b. So this omega b is something, corresponding FB is 11, in the hertz scale is 11.1 gigahertz. Anyway, the backward scattered light is downshifted in frequency, and that is again decided by the acoustic velocity. So when you heat up the fiber, or when there is a change in the fiber, the acoustic velocity changes, and when the acoustic velocity changes, the omega b changes, and hence you can find out what is the specific value of the temperature and strain. So we have already seen the phase matching condition. Now, is there a spectrum associated with the Stokes? So in the sense that we know that the Stokes, the acoustic waves are what are generating the Stokes line. Now these acoustic waves actually decay. So you had a pump and the Stokes, which is generating a beat, there is a grating. So essentially you have the acoustic wave propagating with in the forward direction along with the pump with the frequency omega. But these acoustic waves, whenever you generate these acoustic waves, they don't stay forever, they don't live forever. They decay with a rate, let's say TB. So in the time domain, you can explain this as it has a the strength of the acoustic waves decays as e power minus t by tau b, which means the gain associated, the gain as in the gain associated with the scattered light, that also now will have a frequency spectrum which is characteristics of the time domain decay. Now you know an exponential decay would correspond to a frequency domain picture of Lorentzian. So which means that the gain spectrum G is a Lorentzian, which can be described as the peak value at this omega b divided by 1 plus omega minus omega b the whole square TB square, which means the Stokes gain, you can represent it as a Lorentzian spectrum, right? Lorentzian spectrum whose width is decided by 1 by TB. So center frequency is omega b. This is 11.1 gigahertz is what we had calculated, or FB is corresponding to 11.1 is what we had calculated. But the width is decided by the decay time of the phonon, and that's also a material dependent quantity. And that decay time is about, corresponds to a width of about 30 to 100 megahertz in different kinds of fibers. Okay. This gain spectrum, of course, as we said, it is sensitive to strain and temperature. So when you strain the fiber, it will start moving forward or in the reverse direction. Actually, when you increase the temperature, the frequency shift increases, so the wavelength shift actually decreases. The next thing is to look at the threshold, SBS threshold. We already told you how to understand the process of conversion from spontaneous to stimulated effect. It turns out that if you really work out the math, the threshold power corresponds to approximately 21 multiplied by effective area divided by the peak gain multiplied by L effective, right? So we are not deriving this, but we will understand that the threshold is directly proportional to the area. It is inversely proportional to the effective length. We already defined what effective length is. Effective length is 1 minus e power minus alpha L divided by alpha, where L is the physical length of the fiber. The value of GB is roughly about 5 into 10 power minus 11 meter per watt. It means that as you increase the length of the fiber, the threshold actually decreases. So you will have the stimulated process happening at lower powers. It also is found to actually increase with the effective area of the fiber, but in case of a standard single mode fiber, the area is constant. But the other thing to note is also that all the phenomena that we have described until now for stimulated Brillouin scattering is assuming that pump is a narrow line or with the center frequency omega p. We never consider the line width of the pump. So one more detail is that the threshold actually decreases. Threshold increases with the increase in line width of the source. So the threshold is actually 21 A effective divided by GB L effective times 1 plus delta nu divided by delta nu b, where delta nu is the line width of the source and delta nu b is the width of the Brillouin gain spectrum, which is 30 to 100 megahertz. So if you have a source of larger line width, it means that the Brillouin threshold will start increasing. This is easy to understand because when you have a larger line width, you have multiple omega p's. You can think of it as multiple omega p's in the system. Each of those omega p has to phase match. So the effectiveness of the process starts reducing. And hence in a communication system, whenever we are trying to find out what is a threshold, Brillouin threshold, you should not really use this relation because this relation assumes that the line width is delta function. Whereas you should be using this relation, and this delta nu is the delta nu after modulation. So if you are doing a modulation of about 10 Gbps, it means that effective optical spread is 20 gigahertz. This delta nu would be 20 gigahertz. So your PTH is equal to 21 A effective by GB L effective times 1 plus 20 gigahertz, and let's take 100 megahertz. So with respect to unmodulated source, the threshold has actually increased. The consequence of Brillouin scattering is that if you send in light through optical fiber and you keep looking at what comes back, right? Let's say we have a device. We will talk about this device very soon, but this is a circulator. If you look at what is the power that comes back in the backward direction, because you know that the Brillouin scattering is supported in the backward direction in case of an optical fiber. And let's say you look at what is the transmitted power which is reaching the receiver. This is the reflected power. And this is the input power. What you will see is that as your input power increases, the transmitted power goes on increasing, But whenever the Brillouin scattering sets in, the reflected power will start doing exponential or the reflected power will start increasing very rapidly after the input corresponding to the threshold power, and beyond that, because you need to respect power conservation, the transmitted power will start saturating, which means you may be pumping in more and more power into your fiber, but that's not reaching the transmitter. It is actually getting back to the source, which is not a good idea, not just because you're not transmitting, you're wasting away all that power. All that power is actually coming back and hitting your laser, and that destabilizes your laser. Okay, it's a Brillouin threshold which will be the first nonlinear effect or the lowest, the nonlinear effect which has the lowest threshold. And this is what limits the power that can be given at the input of a fiber. Because if you exceed the threshold, what happens is the power simply does not reach the receiver, it just comes back. Okay, and to give you an idea of what is this threshold, for an unmodulated source for a length of fiber, 80 kilometer kind of span of fiber, you can calculate this threshold comes out to be about 10 dBm. Okay, and to keep a safer margin, we said that we will always operate at power levels. This is considering modulation. Of course, there could be small changes when you change the bit rate, but to be on a safer side, to provide sufficient margin that in your link design, you'll always keep your input power roughly about 0 dBm or less than 0 dBm. This is what resulted in the 0 dBm limit to the transmit power in a fiber optic communication system.